Welcome back. Now, in this lecture, we will be continuing with our lifting machines, and now we are going to discuss the eighth lifting machine mentioned in your syllabus, that is Weston's differential pulley. The Weston's differential pulley block as a two-dimensional diagram is shown here in this figure. Although it should be apparent how the actual configuration is, but again, in order to ease your understanding, I will draw a slightly tilted figure of the complete block, or rather, we should say, I am going to draw an isometric image of the Weston's differential pulley so that your understanding improves. This is how exactly the Weston's differential pulley is going to look. It is basically a stepped pulley block. A stepped pulley block means a single solid arrangement which has two steps in the pulley. And if you pay attention, even the previous models of pulleys and axles or wheel and axles that we have studied, they are also basically stepped pulleys. For example, the first category of wheel and axle was the simple wheel and axle. Now, please mind it that I have deviated my talk a little bit from the actual topic of discussion, that is Weston's differential pulley. Right now, I'm not discussing it. I'm just comparing Weston's differential pulley with what we have studied earlier. So, a simple wheel and pulley arrangement was made like this. This was the axle. Sorry, this is not pulley here. This is wheel and axle. But rather, if you see it in a different perspective, axle, wheel, they are all basically different pulleys. An axle is a pulley whose length is significantly long, and it can be uh, presented as a long cylinder. Whereas a pulley might be having different diameters, but the width of the pulley is generally thinner. So whenever you see a structure like this, you say that this is a pulley. And whenever you see a structure like this with a long body, then you say that this is an axle. But basically, both of them are pulleys. An axle is a pulley having a long length along the cylindrical centroidal axis. That's all. Otherwise, they are both pulleys only. So anyway, this was the simple wheel and axle. Then we had the differential wheel and axle. Differential wheel and axle differs from the above simple wheel and axle in a way that the axle itself is stepped. So there is the first step of the axle. This is the second step of the axle. And at the end of this is fixed the main wheel where the effort is applied. So basically, if you look at it, this whole block is a single pulley block having three steps. Step number one, step number two, step number three. So this is a pulley block having three steps. This is a pulley block having two steps. So in a simple wheel and axle, you have basically a pulley block with two steps. In a differential wheel and axle, you have a pulley block with a three step. And this is Weston's differential pulley. So the arrangement of Weston's differential pulley, as you can see and compare, is exactly similar to that of a simple wheel and axle. See, the only difference is that in the case of a Weston's differential pulley, my axle is a little bit shorter. If I cut this axle from here and remove this part, then you see what remains is the main configuration of your Weston's differential pulley. So starting from here and going back to the image, this is how it is going to look when you look at it from the front. What I'm saying is, if you come to the front of this is your eye, and if you look at it from the front, then this stepped pulley or of the Weston's differential pulley is going to look like this. See, this is wheel number one, or rather step number one, and this is step number two. So you can say these are disc number one and disc number two, which are solidly attached to each other. You have to remember that these two are not separate. They are one single block with step. Okay. So this one is step number one. This is step number two. And when you look at it from the front, this looks like what is shown in the figure. And now what you do is you take a long piece of rope, okay, and you tie this end with the other end so that this whole rope becomes a loop. So you have tied this and made the whole rope in the form of a loop. And now what you do is you tie the loop over this whole block of the stepped pulley in such a way so that, see, now I will trace the complete path of the loop that we have tied around this block. This loop is going like this. It starts from the larger block, comes around, goes to the lower block, winds up the whole way around, and comes down, takes a loop, and goes back to the larger pulley. This is how it is completely wound. And at the this nape, which is forming below, another small movable pulley is attached, and with this movable pulley, the weight is attached. This is the configuration of your Weston's differential pulley. Okay. So once again, I will explain what is happening here. You take a single loop of rope, complete circle it forms, the loop. You start it by tying it around the upper block, loop it around, bring it down, take it on to the second or the smaller diameter pulley, move around it, bring it down, make a loop, and return it to the larger pulley. And since it is one single rope, this is coming and getting connected over here. So you see this single rope is simultaneously covered over the larger as well as the lower pulley in this way, as I have shown over here. And at the loop that is forming at the bottom here, you place another pulley. This is a movable pulley, and you attach the weight to the center of the movable pulley. Now see what happens. The effort P is applied along this length of the rope. Now you pull the rope from here. When you pull it from here, what happens is this whole block starts to rotate. See, this is how it is coming. The rope is tied like this, and you are pulling it downwards. So what happens is the whole block, the upper block as well as the lower block, since they are rigidly connected to each other, they both start rotating in the direction as shown in the figure. And now, since both 1 and 2 are rotating, 1 is rotating in this direction and 2 is also rotating in this direction. So what will happen is, when the upper block or the larger block rotates, the rope will be pulled up from this direction. See, because it is looped like this. So when you are pulling it from here, this rope will climb upwards. But this rope being pulled, as you can see, is being released through this path to the lower pulley. So what will happen when the rope is released to the lower pulley or the smaller pulley? It will wind around this and it will be released downwards to the weight block here. So basically, if you have understood the mechanism of how one single rope wound around two step pulleys can simultaneously pull out the rope and provide the rope at the same time. So here what is happening, just look at this junction, what is happening here. rope is being pulled upward from this arm and rope is being supplied back from this arm. But the rate at which the rope is being pulled and the rope is being supplied, they are different. So once again, what we will do is we will consider one revolution or one rotation of the complete block. Now, if you look at the block, in one complete rotation of the block, block number 1 and block number 2, since they are connected rigidly to each other, they will both cover one single rotation. Okay, the diameter of the second or the lower block is small d, the diameter of the larger block is capital D. So in one rotation, what will happen is the larger block will travel a total circumferential distance. See, this is one circumferential distance. Okay, a total circumferential distance of pi into capital D will be covered by the larger block, or let us say disk number 1. This is the total circumferential distance traveled. In other words, I can say if the circumferential travel of the larger block is pi d, then that is exactly the amount of rope that is coming out of this part. So this eventually becomes my small y. And what is small y? Small y is nothing but the distance traveled by the effort arm. So you can say that if effort is applied at this point of the rope, then in one complete rotation of the block, pi d amount of rope will be coming out from here. So this is fixed. Y is pi d. The effort arm is moving by pi into d. Okay, wait a minute. Now, since in one complete rotation, you are collecting a rope of pi d from this end, from where is it going to be supplied? You see, this rope is coming from here. So if I say that in one complete rotation, pi d amount of rope came from this end, that means pi d amount of rope must have gone upwards from this end. So you can say that pi d is the total amount of rope that was pulled upward from this arm. Now at the same time, look at the smaller block. In one rotation, the smaller block will cover a circumferential distance of pi into small d. And since the smaller block, while rotating, is supplying rope to this end, so we can say that in one complete rotation, the second block supplies a rope of pi into d, but this time small d. And now we have a situation in which, in one complete rotation of the whole structure, pi into capital D amount of rope is being pulled up and pi into small d amount of rope is supplied downwards. Okay, so with this situation, I can conclude logically. I will take away all the construction from here so that we can start fresh. Now we have this situation. See, pi into capital D amount of rope is going upwards per rotation. Pi into small d amount of rope is coming down per rotation. So what can I say about the climb of the center of this movable pulley in one rotation? I want to find out what will be the total upward distance x traveled by the center of this pulley. Why do I want to find this? Because the travel of this center of this pulley in the upward direction is exactly the distance traveled by the weight itself, because the weight is rigidly attached to the center of this pulley. And this is what I'm interested to know, कि ये weight कितना travel करेगा. P का travel तो पता कर ही लिया अपन ने. The travel of P or the effort arm was pi into capital D in one rotation, obviously. Everything is being seen from the perspective of one single rotation of the complete system. Now again, applying the logic of a movable pulley, I can say that if pi d is being taken away from this pulley and pi small d is given back to the smaller pulley from here, then the difference of these two will be the eventual, sorry, difference of these two divided by 2 will be the eventual travel of the center of this movable pulley in the upward direction. Why this is being divided by 2, this was explained in the previous lecture. So if you are seeing this lecture without covering the previous lecture, you will have to go and look at the previous lecture to understand why the total upward travel of this movable pulley will be the half of this quantity. So I can say that my x is this. This is my y. Y is equal to pi d and x is equal to pi d minus pi d by 2. And if you look at the relation of velocity ratio, because velocity ratio is exactly what we are after, we want the velocity ratio. Velocity ratio is distance moved by effort, that is y, divided by distance moved by load, that is x. So the ratio of y by x as determined here will be pi d upon this. Again, the pi will cancel out, 2 will go up, and eventually you have this relation to remember. Now, please see, this is exactly the same relationship that we developed here, or here for this matter. So this is capital D by D for the differential one, yes. For Weston's differential pulley and wheel and differential axle, the velocity ratio has the same relationship, almost the same relationship. Since there are only two blocks here, it is 2 capital D upon capital D minus D. And since there were 3 blocks here, it was 2 capital D upon small d1 minus d2. So the relationship is almost similar. It's easy to remember. Whenever the word differential comes in, you remember that a velocity ratio formula like this is going to come. Okay. So eventually we have developed the equation for velocity ratio. Capital D is the diameter of the larger disk, small d that of the smaller disk diameters. Okay. Now once again, mechanical advantage upon velocity ratio can be found. Mechanical advantage you write as W by P. So mechanical advantage divided by this expression of velocity ratio, you rearrange it, you get this. And once again, you don't have to remember this formula, not at all. Why? Because you just need to remember the formula for velocity ratio. Mechanical advantage is always going to be treated as W by P. And you just divide mechanical advantage with velocity ratio, you will get the expression for efficiency. So this task can be achieved when you are writing the exam itself. You don't have to remember this formula. It will automatically come. The thing that you have to remember is that of the velocity ratio. So it's 2 capital D upon D minus D. Now, sometimes, let me just take out all this construction from this page. There is an alternative to this formula also. Now you see, instead of the velocity ratio being written as 2 capital D upon capital D minus small d, it is expressed in the terms of number of teeth on the sprocket. Now let me explain what is the meaning of this. Look at this figure. See, there is always a problem with pulley and rope. You know, the problem is when a pulley and a rope are used, there is a problem of slip. The rope can slip over the smooth pulley. This surface becomes smooth after a lot of usage, and when you start pulling from this, the rope starts to slip a little on the pulley. So this actually makes you lose your mechanical advantage, as well as the amount of effort is also wasted. More time is required to pull the weight. So sometimes what people do is they use a sprocket. Now you need to understand what is the meaning of a sprocket. Sprockets are used with chains. Now, I'm pretty much sure that everybody at some point of time must have had a very good look at the sprocket and chain arrangement of your simple bicycle. It's a simple mechanical artifact that is available in almost every household, and almost every person as a kid must have had a chance to ride a bicycle at some point of time. Now, the bicycle consists of the mechanism of the bicycle consists of a sprocket. Sprocket is something that looks very much like a gear. So, this is how the sprocket looks. But then you might also wonder, if it is basically a gear, why are we not calling it a gear and why are we calling it a sprocket? Because a gear generally has more width. So the tooth of the gear are like this. The gear teeth will look like this. In other words, we can say that this width of the gear teeth is significantly larger. Okay, but in the case of a sprocket, it will have the same tooth and gap arrangement, but it will be much thinner like this. So this is the basic difference between a sprocket and a gear. So you can say that a sprocket is nothing but a gear only, but with the basic difference that the sprocket will have the width of the teeth which are considerably thinner than a gear. So sprocket is basically the name given to a gear with less thickness. So now you can see that the arrangement that is attached to your bicycles is a sprocket and chain arrangement. Now, where is the chain attached? The chain is attached over the sprocket, and the chain has links like this. Like this. So this is a chain and sprocket arrangement. Now the advantage with the use of a chain and sprocket arrangement instead of a rope and pulley arrangement is that you can totally avoid the concept of slip. So there is no slip in the case of sprocket and chain arrangement. So sometimes, or rather I would say most of the times, if somebody decides to construct a Weston's differential pulley, they would not make use of a rope and pulley arrangement. Instead, they will make a Weston's differential sprocket and chain arrangement. They will eliminate the pulley from here. So they will get a sprocket and chain arrangement. So what is the difference here? The rope is replaced by a chain, and each of these discs is replaced by a sprocket. The rest of the concept remains the same. See, now we have a sprocket here, we have a sprocket here. Both the discs have been taken away, and one larger sprocket and a smaller sprocket have been placed. And instead of the rope, you take the chain. The chain arrangement is taken. So what is the implication of this change on the formula? It's not much different. If you look at it, I take a sprocket which has some certain number of teeth on it. Okay, it's basically a gear, so you can say that it has some certain number of teeth over it. You take another sprocket which is smaller in diameter, and again you have the teeth over the sprocket. Now what can you say about the number of teeth on this sprocket n1 and the number of, okay, let me not take it as n1 since your formula is t1. Let me say the number of teeth on the first sprocket is T1 and the number of teeth on the second sprocket is T2. The diameter of the larger sprocket is D1 and the diameter of the smaller sprocket is D2. See, there is no exact correlation that you might recall right now, but one thing is sure. If D1 is greater than D2, then definitely with 100% surety you can say that the number of teeth on D1 will be definitely greater than the number of teeth on D2 or the smaller sprocket. Apart from that, you can also claim with almost certainty that the number of teeth on any sprocket will be somewhat directly proportional to the diameter of the sprocket itself. Because the larger the diameter, more the number of teeth. Smaller the diameter, lesser the number of teeth. So in a way, the correlation between the number of teeth and the diameter of the sprocket is simple, that it is directly proportional. And if it is directly proportional, then what you can do is in all the expressions that you have developed over here, velocity ratio in terms of pulleys taken for your drive is capital 2 capital D upon D minus D. So instead of capital D, you simply replace it with the number of teeth on the larger wheel. So this will also be number of teeth on the larger wheel. And instead of smaller diameter, you simply take the number of teeth on the smaller wheel. So that is the only replacement that you require in case your Weston's differential block is constituted with the help of sprockets and chain instead of pulleys and rope. So see, all these expressions are simply replaced. Velocity ratio instead of 2d upon d minus d, it is 2t1 upon t1 minus t2. No problem. Efficiency is again W by P into this expression. Again, you replace this capital D and small d with T1 and T2. This 1 is not present here. This is a printing mistake. It is only T1 minus T2 upon 2 T1. This will be T1. So in the text that I have sent you, please make this correction. Since I have copied it from the textbook itself contains some error like this. So you correct it. It is capital D, replace it with T1. Small d, replace it with T2. That's it. So the formula will not change. It's simply a replacement of diameter with number of teeth. That's all. So the problem that can come in your examination might involve any of these quantities. For a Weston's pulley block, they might instead give you the number of teeth on the two blocks instead of the diameters of the block. So you should not get confused कि भाई ये teeth कहाँ से आ गए. तो अब से कभी भी teeth का concept आएगा तो आप तो simply ये समझ लेना कि diameter का अगर formula याद है तो diameter हटा के teeth लगा दो वहाँ पे, बस काम ही खत्म. That's it. Okay. And now with this we come to the conclusion of this one also, Weston's differential pulley. And now I will tell you, or rather ask you to do some exercises on your own. At the end of this lesson, I have already given you practice questions, solved problems number 8.1 to 8.11 from Engineering Mechanics by D.P. Sharma. This textbook is already with you guys. You can start at page number 343 of the textbook. You will directly get to the set of these problems. Now, for the set of the lifting machines that we have just learnt, I will just give you a guidance on which problems are associated with which type of lifting machine. For simple wheel and axle, please refer problem number 8.1. See, these are all solved problems, and in 99% of the cases, they are simply the application of direct formulae. So I'm not going to waste a single minute in explaining those very, very simple problems. Since already a lot of detail has been given to you in the form of video lectures, I want you to go to these problems and just read them. And it would be much better if you can, instead of just looking at the problem how they have solved it, if you can just read the question and try to solve it on your own by taking the formula only into consideration, then it would be very good. That is the best way to prepare for your examination. And if you don't get the right answer, you look at the solution. It is a solved problem. Okay, continuing further, for wheel and differential axle, this was the second type of lifting machine involving wheels. For wheel and differential axle, please refer problem number 8.4 and 8.5. Again, both are solved problems. And finally, for the one that we studied right now, Weston's differential pulley, please refer problem number 8.6. So these are the problems that you have to study for these topics. 8.1, 8.4 and 5, 8.6. This will cover simple wheel and axle, wheel and differential axle, Weston's differential pulley. These are very simple problems. Okay, so please make sure that you at least practice some problems like this. We will stop the lecture here, and in the next lecture we will take up a new concept of worm and worm wheel. But for now, I stop here. Thank you.